Hi everyone, my name is Nihan and I'm a postdoc at Vanderbilt University. Today I will be talking about modeling the galactic ultra-compact binary neutron star population. So to give you a quick overview of my talk, we want to use population modeling to constrain the number of binary neutron star systems in the Milky Way which have orbital periods less than 15 minutes. We also want to estimate the probability of detection of at least one of these ultra-compact binary systems with the current radio pulsar surveys. And then we want to estimate an optimum integration time for radio surveys that will maximize their sensitivity to these ultra-compact binary systems. And the reason we are concentrating just on the ultra-compact binary systems is because these are really promising sources for LISA and could potentially be directly detected within the first few weeks of operation of LISA. So how do we find binary neutron star systems? We find them by using pulsars. So a majority of the known neutron stars and binary neutron star systems have been observed using pulsars. So pulsars are rotating neutron stars that emit beam radiation in a fashion similar to a lighthouse. And this is shown in the illustration on the right hand side, where as the beam radiation crosses our line of sight, we see a bright pulse of emission as shown on the bottom panel. The spin periods for pulsars typically range from about a millisecond to a few tens of seconds. Pulsars also have a power law spectrum, which makes them brightest at low radio frequencies. As a result, the largest pulsar surveys so far have been carried out using radio telescopes from around the world. And I'm showing pictures of a few of them on the right hand side. So how do we model the UCB pulsar population? Modeling the pulsar population centers around the radiometer equation shown here on the right hand side. The radiometer equation quantifies the sensitivity or the signal to noise ratio that any radio pulsar survey can achieve for a given type of pulsar. So the sensitivity depends on the telescope and survey parameters such as the gain G, system temperature Tsys, integration time Tint, and the bandwidth P. The sensitivity also depends on the pulsar parameters itself, such as the flux of the pulsar S, the pulsar spin period Ps, the pulse width W, and the orbital parameters of the BNS system, which manifest themselves through the orbital degradation factor gamma. The signal-to-noise ratio is affected by a host of propagation effects as the pulsar's emission travels towards the Earth. And it is also affected because of the binary motion of the pulsar in the BNS system. This effect of binary motion in the BNS system is most relevant for trying to detect these BNS systems. So let's take a look at that. So the pulsar's motion around the companion causes Doppler shifts in the observed spin period, which in turn reduces the signal-to-noise ratio. This is shown in the image on the right hand side, where in the left panel we can see that if this motion of the pulsar around the companion is left uncorrected, it causes this smearing in the observed pulse profile, which in turn results in a reduced signal to noise ratio. However, if we know the orbital parameters of this system accurately, then we can remove this effect of the binary motion of the pulsar and recover a very sharp and strong pulse profile, which in turn increases the signal to noise ratio. However, typically when we are searching for these systems, we do not know the orbital parameters beforehand. And as a result, despite our best efforts, some amount of smearing is still left over in the dataset. The extent of this smearing depends on orbital parameters like the orbital period, the eccentricity, the mass of the companion, as well as the period of the pulsar and the survey integration time Tint. And the amount of smearing that's left over in our dataset is quantified in the orbital degradation factor gamma that we saw in the radiometer equation. So to simulate the pulsar population, we use the PsrPopPy software package that was developed by Bates et al. In 2012. However, PsrPopPy originally did not have the functionality to calculate the orbital degradation factor for any given type of BNS system. As a result, as part of this work, we developed a new neural network implementation for the calculation of this orbital degradation factor gamma, and then we plugged that back into PsrPopPy so that PsrPopPy can now handle simulating BNS pulsar systems. So the way we do this pulsar population synthesis is structured in the form of a Monte Carlo simulation. So first we generate a population of binary pulsars n total. We then calculate the degradation factor for each pulsar using our neural network. We then calculate the signal to noise for the pulsars using the modified radiometer equation. And then we see how many pulsars have a signal to noise ratio that's greater than the threshold signal to noise ratio for the given survey. And these pulsars will then be detected in that survey. and we count the number of detected pulsars in the variable n orbs. Then we repeat this whole process by generating a new population of binary pulsars with a different size n total. And here in the table on the right hand side, I'm showing some of the pulsar surveys that we use in the simulation, and these are some of the largest surveys that have been carried out so far. So once we do this analysis, a really strong trend begins to emerge in that the average number of detected pulsars quantified here by lambda in equation 1, it turns out that lambda is directly proportional to the size of the population that we generate. So lambda is directly proportional to n total, where the constant of proportionality alpha, as shown in equation 2, is the one that encodes the properties of the pulsar population and the pulsar surveys that are being carried out to detect these pulsars. As a result, once we know the value of alpha, then assuming the right likelihood function, we can then calculate the probability distribution function of the size of the population for any given type of BNS pulsar system, and that's shown in equation 3. One thing that I do want to point out is that the size of the population that we are modeling here is the size of the population that's beaming towards the Earth. So in doing these simulations, we implicitly assume that if we had an ideal radio telescope, it would detect all of the systems that we're generating in the simulation, which in turn means that all of these systems are beaming towards the Earth. However, in real life, pulsars need not necessarily be beaming towards the Earth, and their beams could just miss the Earth's line of sight completely. So to account for this, we need to introduce an extra beaming correction factor, which is essentially a scaling factor which scales the size of the population that we derive to get the total size of the population of a particular type of BNS system. So here's a brief summary of the setup of the pulsar population synthesis simulation. And the only thing that I want to point out explicitly is that we constrain the orbital periods to be less than 15 minutes since we are interested in the ultra-compact binary neutron star population. So let's take a look at some results. So given that there are no detections of ultra-compact binary systems consisting of a pulsar yet, we can only place upper limits on the size of the population. And that's what's shown here on the right hand side, with the top right panel showing the upper limit on the number of UCB neutron star white dwarf systems, which comes out to about 800 systems. And on the bottom right is the upper limit on the UCB double neutron star systems, which comes out to about 1000 systems. And again, I just want to remind you that this is the upper limit on the number of systems that are beaming towards the Earth. So to get the total size of the population, we would need to scale these numbers up by the beaming correction factor. However, this factor is highly uncertain, and as a result, we don't do that in this work. We also want to estimate the probability of detection of at least one of these UCB pulsar systems with the current radio pulsar surveys. So to do this, we assume that the number of UCB systems in the Milky Way corresponds to their upper limit that we derived on the last slide, and then we calculate the probability that the radio surveys will detect at least one of these systems. And that's what's shown here on the right hand side, where the y-axis is the probability of detecting n systems, and the x-axis shows the n systems detected. And so as we can see, the pulsar surveys that are being done at the Arecibo radio telescope in Puerto Rico, shown here in the brown and green, are the ones which have the highest probability of detecting one of these ultra-compact binary neutron star systems, clocking in at about approximately 50%. Building on this, we want to see if we can optimize the current radio surveys for the detection of an ultra-compact binary pulsar system. So since the orbital degradation factor depends on the integration time, we can tune the radio surveys integration time to maximize the signal noise for these UCB systems. So to motivate this problem a little further, on the right hand side on the top, I have the radiometer equation that we saw earlier, but it's split up into two parts where F1 quantifies all of the properties outside of the degradation factor gamma. And on the plot on the bottom right, I'm showing the evolution of both F1 and gamma as a function of the integration time. And since this is on a log-log scale, we can see that F1 scales linearly with an increase in the integration time. On the other hand, the orbital degradation factor shown here in the orange has a turnover corresponding to a particular integration time that's unique to this type of BNS system. As a result, when we put together F1 shown here in the blue and the orbital degradation factor gamma shown in the orange and calculate the total signal to noise ratio as a function of the integration time, we can see that there is the formation of a particular peak corresponding to this type of DNS system. And so when we want to search for these kinds of BNS systems, we would like our integration time to be as close to this peak as possible. However, since each unique BNS system will have its own slightly unique peak in this signal to noise function, instead of just deriving one number, we need to derive a range of numbers which give the maximum signal to noise ratio for a particular type of BNS system. And so once we do this calculation for ultra compact binary pulsar systems in particular, we see that integration times between 20 seconds and 200 seconds will maximize the signal to noise ratio for detection of these UCB pulsar systems. So to explicitly show that this does indeed improve the detection probability, what we do is we use an optimum integration time of 50 seconds for all of the radio pulsar surveys that we've considered so far. And we calculate the probability of detecting these UCB systems using this optimum integration time. And the results are shown in the plot on the right hand side, where the y-axis shows the increase in the probability of n systems being detected by a given pulsar survey, and the n systems detected is on the x-axis. And we can see that using an optimum integration time of 50 seconds leads to an increase in the detection probability across all the surveys. And especially the highest increase in the detection probability can be seen in the P-alpha survey, shown here in the green, which is one of the surveys being done at the Arecibo Radio Telescope. So putting this together with the results that we saw a couple of slides ago, this brings the total probability of P-alpha detecting at least one of these UCB pulsar systems to about 80%. So with the right integration time, it is very much possible that we can detect at least one UCB system before LISA is scheduled to launch in the early 2030s. And finally, I want to give you a quick overview of some future work that we are planning to build on the results from this analysis. So first, we want to search P-alpha and other surveys archival data using these optimum integration times to try and see if we can find one of these ultra compact binary neutron star systems. We also want to perform a similar analysis to estimate the size of the pulsar black hole binary system population in the Milky Way, and this includes pulsars around Sagittarius A star. And finally, we want to combine PsrPopPy with BNS evolutionary simulations such as Star Trek, MOBSE, etc. to simulate astrophysically motivated population sizes, merger rates, and detection prospects. So for example, we have already started to integrate Star Trek simulations with PsrPopPy to estimate a neutron star black hole merger rate for LIGO, and this is a work that is currently in prep and should be submitted in the near future. So that's it from me. Thank you for listening to my talk, and if you have any questions, please feel free to get in touch with me at this email address. Thank you.